So, welcome everybody to the latest edition of the Pangolin Seminar. Today, Andrea Seppi from the University of Grenoble will speak to us about the Gauss map for nearly-Fuchsian manifolds. So, over to you, Andrea.
All right, thank you very much, Graham, for the introduction, and thank you guys for the invitation. So this is joint work with Christian and Emam, who is finishing last year PhD student in Pavia. So he's a very brilliant PhD student, and he will be on the job market soon, I think. So just a little advertisement in case this can be useful for someone.
Are all his positions available in Rio de Janeiro if he's interested?
Very good. Okay, I'll let him know. So let me start with some motivation. So basically, the main motivation which we should keep in mind behind this work is this class of hyperbolic tree manifolds, which was introduced by Uhlenbeck, essentially, which are called almost Fuchsian manifolds. And these were studied by several authors. I will give the definition in a minute. Just let me remark that these are three-dimensional hyperbolic manifolds. Actually, the results, so we can, of course, keep in mind this motivation throughout the talk, but the results I'm going to present will all true for hyperbolic manifolds of any dimension. So actually, I will borrow this terminology, almost Fuchsian manifold, for instance, and the other definition I will give from dimension 3, but we always extend this to any dimension. So this class of hyperbolic tree manifolds are defined like this. They are complete, and topologically they are a product of a closed manifold M of dimension n, let's say, times the line. So such a hyperbolic manifold endowed with a hyperbolic metric H is called almost Fuchsian if it contains a minimal hypersurface, so a hypersurface of vanishing mean curvature, which is homotopic to M cross 0, so a sort of horizontal slice, and has principal curvatures strictly contained between -1 and 1. So again, this is the definition which was originally given in dimension 3, but we will use this definition in any dimension. Another definition, as larger a priori class, is the class of nearly-Fuchsian manifolds. So here, we do not assume that the hypersurface is minimal. So almost Fuchsian case, sorry. In the almost Fuchsian case, we had the minimal assumption. Now, in the definition of nearly-Fuchsian manifold, we just require that there is a hypersurface homotopic to a horizontal slice with principal curvatures in -1, 1. I will discuss a little more later about some properties of it.
So nearly-Fuchsian doesn't imply almost Fuchsian then?
Almost Fuchsian implies nearly-Fuchsian.
Right, yeah, definitely.
The other one is not known.
There's no barrier arguments.
This is a very good question, and I will mention something more about this question. But as far as I know, this is still an open question at the present time, okay, whether these two classes coincide.
Okay.
And finally, the last class, maybe you're more familiar with this, is the class of quasi-Fuchsian manifolds. So these are just product M cross R, such that there is a compact and geodesically convex subset inside the manifold. So a sort of, you can take the smallest such subset, and this is usually called the convex cone. Okay, so I had to forget. Okay, so there are some implications between these. Let me just to specify, to complete the definition, what are the principal curvatures, where the principal curvatures are just the eigenvalues of the shape operator, which is defined in a general Riemannian manifold for hypersurfaces minus the derivative of the normal vector. And you might wonder, why do you require -1, 1, this interval in which you want your principal curvatures to be contained? Well, basically because 1 is the value of the principal curvatures of a horosphere, or -1, depending on which normal vector you choose. So you might wonder, why did that number 1? Well, basically that's because it's the curvature of a horosphere. There are some implications, as I was saying, between these manifolds. So almost Fuchsian, this one is kind of trivial. Almost Fuchsian implies nearly Fuchsian. And the other one, as I said, is not known. I will discuss more about that. But for these other implications, this is sort of well known. So basically, I can give you a sketch of the argument. The idea is that if you have a hypersurface, which contains basically all the topology of the manifold and has principal curvatures contained between -1 and 1, well, then you can prove that you can find a region like that, which is an equidistant region. So it's a region of points at distance at most some constant c from the hypersurface. And you can prove that if you take C sufficiently large, then this region is compact and geodesically convex. And therefore, your manifold is quasi-Fuchsian. And okay, and important, somehow you might wonder, why do you care about this manifold, almost Fuchsian, nearly Fuchsian? Well, at least one of the motivations is that under such an hypothesis, if you know the first and second fundamental form of your hypersurface, then basically you can reconstruct the geometry of the entire manifold. So the geometry of the entire manifold is determined, and it's also very easily described in terms of just the embedding data of the hypersurface. And as I was saying, we don't know at the present time, at least I don't know, whether these two classes are actually equal. There was some suggestions. So basically, Ben Andrews, in a sort of survey paper, at the end gives a hint and says that there is a very interesting geometric flow that one could consider. And basically, the idea is to evolve. So sigma t is a path of immersions. So you try to start with a sort of hypersurface, and you evolve according to the normal vector multiplied by this function, which is the sum of the hyperbolic inverse tangents of the principal curvatures of your hypersurface.
When did Andrews suggest that flow?
Well, he was okay. I'll say something more about this, but basically, he was in this survey paper. He cares about the case of the tree sphere, and he wants to evolve some sort of tori in the tree spheres, the tree sphere. And in that case, you have the usual arctangent, right here. And then he says, in hyperbolic space, you can consider the hyperbolic arctangent, and this has good properties and whatever. But
I have a feeling, I have a feeling this is related to the almost Calabi-Yau structure of the unitary bundle.
I think it's related. So maybe at the end of the, I hope maybe at the end of the talk, maybe you will have a clearer idea whether it's related or something like that.
It just looks very, very similar to special Lagrangian curvature, which is...
Yes, it is. I think it is. I think it is very much. So in the very last slide of this talk, I will say something more. So in fact, there are two questions which I want to address in this talk. The main question is this one. So we don't know if this class of nearly-Fuchsian is the same as almost-Fuchsian. But the question we started with is, we would like to understand what is if you consider all the hypersurfaces, which have principal curvatures in -1 in your nearly-Fuchsian manifold, well, what can we say about the structure, about the space of all these hypersurfaces with these bounded and principal curvatures? Can we somehow look at them all together? Can we say something about the space? This is very vague for the moment. I will be more precise. And the second question is, well, is the question you're asking, right? So is there some geometric reason, some geometric motivation behind defining this flow in this way? So I cannot, I don't have a proof of the fact that these two classes are coincide, but I understand something more about this flow. I understand that it has a good, it satisfies a very good maximum principle. But if you want to prove that this maximum principle holds, well, there is a sort of algebraic manipulation when you try to do this maximum principle. You have some miraculous cancellation that occurs, but I didn't have a more deep reason why this is the right flow to look at. And so the other question I want to address is there some more geometric reason behind, which is not just computing a maximum principle analytically, why one should be interested in this one should be interested in this flow. And this is, I will say something hopefully at the very end of the talk.
A lot of these PDE people, they're not very good on geometric reasons.
Well, no, maybe it's me that I'm not good enough in PDEs. But
no,
anyway, I hope I will convince you that there is a deep geometry behind considering this.
Yeah.
And I tried that. The way I try to answer these two very vague questions is by looking at the space of oriented geodesics. So the space of oriented geodesics in hyperbolic space. This will be the main playground for our talk today. Okay. Sorry for this title of chapters, which look like a Tarantino's movie. Anyway, I will discuss what is the parakelar geometry of the space of oriented geodesics. So where this story is, here is a parallel story which is starting, and it started with Itchin in 1982, who observed that if you consider the space of oriented lines in Euclidean space, this has a natural complex structure. And this gave rise to a whole theory of people who got interest in space of geodesic, of oriented geodesics, in many settings and many structures. So not only complex structure, but in general, these kind of spaces are symplectic, Riemannian, Kähler, etc. And for us, the fundamental structure is a parakelar structure. I will tell you what it is, on the space of oriented geodesics of hyperbolic space of dimension m. So this space is also endowed with a natural Kähler structure, but for the purpose of this talk, the parakelar structure is more relevant. And what is a parakelar structure? Well, it's the datum of pseudo-Riemannian metric of a paracomplex structure. So what is a paracomplex structure? It's a 1-1 tensor on your manifold, which squares to the identity, not to minus the identity as ordinary complex structures. And moreover, you want to require that the eigenspaces, so the square is the identity, so the only possible eigenvalues are 1 and minus 1, and we require that the eigenspaces of 1 and minus 1 are integrable distributions which have the same dimension. And then there is also a symplectic structure, which is determined by the first two. So as usual, as for Kähler manifolds, two of these three guys determine the third guy. And of course, there is a sort of compatibility. So basically, you want the first, you can express this compatibility by a relation which involves the metric and the paracomplex structure. You want basically that the paracomplex structure is an anti-isometry for the metric. And this implies, well, first of all, this implies that omega is a two-form, is skew-symmetric, and it also implies that the metric has neutral signature, so the signature NN.
Is it possible
excuse me, Andrea?
Yep.
So when you say pseudo-Riemannian, it could be Riemannian, for example?
No, but in this case, so sorry. Since you have this relation, basically the signature is necessarily neutral.
Okay.
I was about to ask a question, but it looks like you're going to answer it.
Okay, so let's now, then you will ask the question again if you like.
But
let's now focus
looks like the answer's on the slide.
Let's now focus on the case of space of oriented geodesics of hyperbolic space, or dimension n+1. I consider dimension n+1 because it's simpler for me. So basically, the space of oriented geodesics in hyperbolic n+1 space identifies, well, a geodesic in hyperbolic space oriented is uniquely determined by the two its endpoints, right? So this space identifies to the product of two copies of the sphere, which is the visual boundary of hyperbolic space, minus the diagonal, because the two endpoints of the geodesic cannot coincide. But for us, it will be more useful to take a different approach and consider our space of oriented geodesics as the base of a certain principal R bundle whose total space is the unit tangent bundle of your manifold. Okay, So let me tell you how this principal bundle is defined. Well, we have an action of the R, which is just given by the geodesic flow. Okay, and this is the action which moves points in the fiber. And let me just stress one point which is very important. So the total space of the unit tangent bundle of hyperbolic space in this talk will have two bundle structures. One is P, and is this bundle map, principal R bundle map with base the space of oriented geodesics, okay? And the other one is the obvious one, is just the usual projection, which will be pi for me over hyperbolic space itself. And these two guys, we must distinguish them very well, let's not get confused, but they will somehow interact in an interesting way. Also, I have to say something more. So I'll denote by chi the infinitesimal generator of the geodesic flow. So this is a vector field on the total space of the unit tangent bundle. And we want to define this parakelar structure on the base, okay, on the space of oriented geodesics. And the idea is that we define all the actors which play in the definition of the parakelar structure. We will define them in the tangent space of every point on a complement of chi in the unit tangent bundle. And then we want to use the differential of the projection to push this forward on the base, okay? And of course, we have to show that this is well defined, that this does not depend on the point on the fiber. But this is the idea. So we basically define the object in the unit tangent bundle on an orthogonal complement to the tangent space to the fiber. And then we show that we can push forward to the base. This is how we will define the parakelar structure. So we'll spend a few slides to introduce more or less properly this parakelar structure. But to do this, I will first need to recall what are horizontal and vertical lifts. So, and also we'll introduce the para-Sasaki metric, which is a sort of variation of the Sasaki metric on the unit tangent bundle. So to do this, basically, let's first recall what the vertical lift is in the unit tangent bundle. So let's take a base point, which is xv. So this is a point of the unit tangent bundle, a point in the tangent vector. V is unit because we consider a unit tangent bundle. And let's take a vector w, which is orthogonal to v. Well, then we can, it's very natural to define the vertical lift of w, because basically the orthogonal to v is just the tangent space to the fiber. So vectors which are orthogonal to v are naturally identified to the tangent space of the fiber over x. And this lives in the tangent space of the total space of the unit tangent. So this is the vertical lift. It's very natural, does not depend on any choice. On the other hand, one can define the horizontal lift, but here you need to make some choice. Basically, you need to make a choice of a connection. And for us, this will be the Levi-Civita connection. And once you pick a connection on your base, in this case, h to the n plus 1, then for every w based at x, you can lift horizontally. Well, I'll just say in words. Basically, what you do is you take w, which is downstairs. You take a geodesic, which has initial speed w, and then you parallel transport your vector v, which is upstairs, along this geodesic. And you differentiate, and the derivative at time 0 is the horizontal lift of this vector w. So this gives a natural horizontal lift, which maps w to its w horizontal, okay, in the total space of the unit tangent bundle. A particular example, basically the infinitesimal generator of the geodesic flow, it's just the horizontal lift at the point xw. This is just the horizontal lift of w itself. This is basically because the tangent vector to a geodesic is parallel along the geodesic. So the conclusion of all this story is that we have a natural, once the Levi-Civita connection is chosen, we have a natural decomposition of the total space of the tangent space to the total space in a horizontal and vertical, horizontal and vertical subspaces. And here what I'm doing, I'm moreover decomposing the horizontal space as the subspace spanned by chi and its orthogonal complement. So that basically both V and this H0, which is the orthogonal complement of chi, identify with the orthogonal of V itself in the tangent space to the base. Okay. So the composition, we have these two subspaces, which are both identified to the orthogonal complement of V, and then the generator of the geodesic flow. It's span. And now we can finally define the Parasasaki metric. The Parasasaki metric, well, the definition is very natural because basically we define it subspace by subspace. So we define this to be if you have two vectors which are horizontal, then you just match them by using the hyperbolic metric on the base. If both vectors are vertical, then you just pair them by using, again, the hyperbolic metric. This would give the Parasasaki metric, but here, sorry, this would give the Sasaki metric, but here we want the Parasasaki metric, so we put a minus sign here. So this minus is a difference with respect to the usual Sasaki metric. And finally, we declare that the horizontal and vertical subspaces are orthogonal. And it's a very important remark here is that the action of the geodesic flow does not preserve this decomposition in horizontal and vertical subspaces. And that might be an issue, but fortunately, the geodesic flow preserves the Parasasaki metric and also, of course, the generator of the geodesic flow. And therefore, we can define our metric downstairs just by taking the Parasasaki metric upstairs, restricting the Parasasaki metric to the orthogonal to the geodesic flow, so the orthogonal to the fiber of this principal bundle, and push this forward by the differential of the bundle map. And by this paragraph here, basically this thing is well defined. Does not depend on the chosen point in the fiber. And in a similar way, one can define what one does to define the paracomplex structure downstairs on the space-oriented geodesic, while we define upstairs on the orthogonal complement of chi. And here is just switching horizontal and vertical subspaces. And it's not difficult to check that these two things are compatible in the sense that J is an anti-isometry for G, and therefore, and it's also integrable. And this I will say a word why this is integrable. And so this gives a parakelar structure. And also the associated symplectic form the associated two form is symplectic. It's closed, and I will say also a word about why this is true. But in short, we can define the structures upstairs and then push forward to the space-oriented geodesics, which is the base of our principal R bundle. And that's why I want to introduce, there's many ways to introduce this parakelar structure in the space of geodesics, but this is the way I want to look at it. And also, I'm ready now to talk about, well, the main object, basically, of our results, which is the Gauss map. So let's now take an immersion, codimension 1, so an immersion of a hypersurface in hyperbolic n+1 space. So U is dimension n. And now it's natural to consider, to associate to such sigma its Gauss map, which takes value in the space of oriented geodesics. What is the Gauss map? Well, this is just a map which takes a point of U and associates to this point the orthogonal geodesic at sigma of x, and we have to pick an orientation. But let's say that U is oriented, we take an orientation of H to the n+1, and therefore we can also induce an orientation of the geodesic. And so this gives an element of the space of oriented geodesic. It's just basically the Gauss map, right? The orthogonal geodesic at every point. And it's useful to consider this map in this unit tangent bundle setting. This map can be seen just as the composition of this lift sigma twiddle, which is just lifting the immersion in H to the n+1 to the unit tangent bundle just by means of the normal vector, and then post-composing with P, which is the bundle map from T1 of H to the space of oriented geodesics. Hopefully this is clear, otherwise do not hesitate to ask questions. And the important thing is that this lift geodesic flow, so it's orthogonal to chi. And now if we try to reformulate this fact in the setting, in the language of principal bundles, this means that basically this lift sigma twiddle, this gives us a flat section of pi over the image of G sigma, or more properly, this is a flat section of the pullback bundle of P by G sigma. Well, flat is with respect to a principal connection on our principal bundle. And what is a principal connection on a principal bundle, on the total space of a principal bundle? In general, this is a one form with a sort of equivariance property. But here, our principal bundle is very simple. The group is just R. So in short, the principal bundle we consider here is just this guy, and this is the guy you have to keep in mind in this talk. So this is basically just a one form, which is given by taking a vector and use the metric to pair it with the infinitesimal generator of the geodesic flow, and this metric is the Parasasaki metric. So this is a principal connection. It's designed in such a way that flat sections with respect to the principal connections, to this principal connection, so these are sections which are tangent to the kernel of this one form, are orthogonal to chi. It's exactly designed for this purpose. And now a remark, just to relate with what I was saying previously, you might wonder, why is this para-complex structure that you defined on the space of oriented geodesic integrable? Well, the integral submanifolds of the +1 and -1 distributions are just the Gauss maps of orospheres. Okay, so these are you can prove directly that this is integrable because you exhibit the integral submanifolds in the sense of distributions. So now the key fact is that if you compute, we have this connection form, which is on the total space of our unit tangent bundle. We want to compute its curvature. Its curvature is just a pullback of omega, and omega was just the symplectic structure on the base, which is the space of oriented geodesics. Okay? So since the curvature in a principal bundle is the obstruction to admitting flat sections, there is an immediate consequence, which is the fact that if you have take an immersion in H to the n+1, take its Gauss map is necessarily Lagrangian with respect to this symplectic form. And that's just because, well, the Gauss map, once you have an immersion, we have this sigma twiddle, which was a lift to T1, and this was a flat section with respect to omega. So over the image of the Gauss map, our principal bundle admits a flat section. So it's flat, so its curvature vanish. And therefore, the image of the Gauss map is Lagrangian. And the converse is almost true. So basically, if we have an immersion in the space of oriented geodesics, then you can recover this as the Gauss map of an immersion in a hyperbolic space, if and only if it is Lagrangian, but this is only local. Okay, so only up to restricting U, then you have a Lagrangian immersion in the space of oriented geodesics. You can see this as the Gauss map of some immersion in a hyperbolic space, but only local.
Do you not have degenerate examples?
Yes, so it can, in general, it can become degenerate. So you can find a map, you can recover a map to the unit tangent bundle, but when you project this down to hyperbolic space, this becomes singular. This is the main issue. Why this is the reason why you can only do locally and not globally.
Okay.
But there's something more that you can say. So if you now go back to our condition of principal curvatures in -1, 1, the interesting thing is that in terms of the parascalar geometry of the space of oriented geodesics, an immersion sigma has principal curvatures in -1, 1, if and only if the Gauss map is Riemannian. So now this is with respect to the pseudo-Riemannian metric in the space of geodesics. Okay, and this is a very nice characterization. This is a nice in my opinion, a nice geometric interpretation of this condition of principal curvature C minus 1, 1. And in this case, we can give a better characterization. So basically, we can give a stronger version of this proposition if U is simply connected. And so the Gauss map, okay, maybe let's read what is written here. If you have a G map in the space of oriented geodesics defined on a simply connected set, then this is the Gauss map of an immersion with principal curvature C minus 1, 1, if and only if it is Lagrangian and Riemannian. So this is an improvement. This is an improvement of this proposition in the sense that we are adding the condition of principal curvature C minus 1, 1, which corresponds to being Lagrangian. But here we really have a global characterization, not only a local one. All right?
But what do you mean by Gaussman is Riemannian?
It's with respect, so remember in the space of oriented geodesics, it's space-like, sorry.
Okay.
In the space of oriented
geodesics,
yeah. In the space of oriented geodesics, we have a pseudo-Riemannian metric of neutral signature.
Yeah, and the image is Riemannian, yeah, okay.
Yes, or if you want, the pullback metric is a Riemannian metric.
Yeah, okay.
Well, this is maybe not as hyper important, but if the induced metric, moreover, is complete, is Riemannian is complete, then both the immersion and also the Gauss map are necessarily embeddings. So this is just to say that this enables us to talk about embedded submanifolds and not just immersions. It's a little better in terms of giving our statements. Okay, so this is all I wanted to say about this geometry of the space of oriented geodesics. Now I'll make a jump back. I'll discuss some more properties of nearly-Fuchsian manifolds. And once this is done, I will finally present our results. So let's talk a little more about the geometry of nearly-Fuchsian manifolds. So basically, remember, a nearly-Fuchsian manifold is topologically a product of a closed manifold M and the real line, okay? And suppose we have an immersion of M inside this manifold, which is basically a horizontal slide. Then we can lift this to the universal cover, and this gives an embedding actually. Or yes, if this is an embedding, there's an embedding of the universal cover inside H to the n plus 1. This is because the nearly-Fuchsian manifold, we can see this as a quotient of hyperbolic space because it's a complete hyperbolic manifold. And this immersion is equivariant with respect to the holonomy representation of your nearly-Fuchsian manifold, which is a representation of the fundamental group of M cross R, which is just fundamental group of M in the isometry group. And here is a picture. Basically, here I forgot to say that I'm assuming that I has small principal curvatures between -1 and 1. Okay. Under this assumption, then you see that the closure of the image of sigma twiddle, sigma is correct. The image sigma is on the universal cover. Its closure is a n-1 sphere topologically in the n sphere, which is the visual boundary of hyperbolic space. And moreover, in higher dimension is not obvious. Moreover, this topological sphere divides Sn in two connected components, which are topologically disks. And the good thing is that the dynamics of the action of the fundamental group is very well described. Basically, we have, of course, a free and properly discontinuous action on the interior of hyperbolic space, and the quotient is our original nearly-Fuchsian manifold. And moreover, this action of the rho, the fundamental group, extends to a free and properly discontinuous action on each of these two topological disks. This is like in quasi-Fuchsian manifolds, but this is true in any dimension. And so we have these two distinguished regions, which is omega plus and which are omega plus and omega minus in the boundary of hyperbolic space. And on each of these, the action is good. And clearly, if our immersion sigma is rho equivariant in hyperbolic space, then also the Gauss map is rho equivariant with respect to the obvious action on the space of oriented geodesics. And actually it takes value. It turns out that the image of the Gauss map takes value in a distinguished region, which is just omega plus times omega minus. So whenever you have an immersion with principal curvatures between -1 and 1, the normal the orthogonal geodesics has one endpoint in omega plus and the other endpoint in omega minus. And therefore we can consider the Gauss map in the quotient omega plus times omega minus divided by the action of rho of the fundamental group. And this is the region which I will call R rho, so the region associated to representation rho. And this immersion in the quotient is indeed an embedding, and it is Lagrangian and Riemannian, just because of the previous proposition which I showed you. But the important thing I want to stress is that this region R rho, sorry, so what happened? This region R rho, it only depends on rho, okay? This region which I define omega plus times omega minus, it does not depend on the embedding with principal curvatures in -1, 1. It only depends on the representation. So basically, we can see the image of the Gauss map of any immersion with principal curvatures in -1, 1. We can see this as an embedded Lagrangian and Riemannian submanifold inside here in R rho. But this is not, you cannot really reverse the construction. So if in the simply connected case, remember, being Lagrangian and Riemannian was the only obstruction to recovering the submanifold as the image of the Gauss map. But here in the equivariant case, this is not true. So the important point is that there are a priori, and I will give you an example in a minute, a priori you can have rho equivariant Lagrangian embeddings in this space, or in omega plus times omega minus, more precisely, which are rho equivariant, but do not come from rho equivariant embeddings in hyperbolic space, okay? And I'll try to convince you of an example immediately in a slide. But just to say that, sorry, it's taking a very long for me to state my results. They're a little technical, but we are almost there. But our results will give a characterization of those, in the equivariant case, in the rho equivariant case, will give a characterization of those hypersurfaces, sorry, not hypersurfaces, so submanifolds, just in Lagrangian and Riemannian submanifolds. Sorry. Well, just the class of Lagrangian and Riemannian submanifolds in this space, which are induced by the Gauss map of an embedding with small principal curvature -1, 1. And now I'm going to give you an example to convince you that rho equivariance in the space of geodesics does not correspond to rho equivariance in hyperbolic space. And the counter example is very simple. I will just give you in dimension 2, so n equal to 1. So consider, here's a picture. Consider just a geodesic in the hyperbolic plane, and consider the family of geodesics which intersect gamma. So gamma is this geodesic. And consider all the geodesics which intersect gamma with a certain fixed angle, θ0, certain constant between 0 and pi. All right. So this gives this is a family of geodesics. So this gives a curve in the space of oriented geodesics, and this family in the space of oriented geodesics, this family is invariant by a representation rho, which is just basically translating in this direction, okay? The family of geodesics is invariant by this representation because, of course, the angle is the same. Now, if we look what happens in the space of oriented geodesics, well, we can give coordinates on our, in this case, basically our omega plus and omega minus, sorry. Omega plus and omega minus are just these two arcs, okay? We can give coordinates on this space, omega plus times omega minus, in the space of geodesics. The coordinates are just the arc length on gamma, which gives the intersection point, and the angle of intersection of our geodesic. And the metric on the space of geodesics is just this pseudo-Riemannian metric, which I'm sure at least half of the audience will be familiar with this metric and will recognize that this is the anti-de Sitter metric. in dimension 1 plus 1. So here, and if the other half of the audience maybe is not familiar with the anti-de Sitter geometry, but you can forget about it. This is just a Lorentzian manifold. Basically the image of this family of, this is now a picture of anti-de Sitter 1 plus 1 space, but just think about it as the space of geodesics. The image of this family of geodesics is just a curve like this, okay? So this is, of course, Lagrangian because, well, in dimension 2, there is no, every curve is Lagrangian. It is Riemannian because if you look at the lines theta equal to theta 0, this is Riemannian curve for this metric. And it is, of course, equivariant with respect of the induced action on the space of geodesic, which is just a translation like that. But this does not come from an equivariant curve in hyperbolic space. This is because if you try to find a curve in hyperbolic space which is orthogonal to this family of geodesics, well, you will, you will end up with a curve like this, okay, which is not equivariant. So if you apply rho of the generator to this curve, you find another curve which is also orthogonal to all these geodesics, but it's not the same. Okay, actually, one differs from the others by evolving by some action of the geodesic flow. This is the guiding idea, in fact, of our results. These yellow curves are not invariant. If you apply rho of 1 to this yellow curve, you find another one which differs by the geodesic flow at some time. And this is the guiding idea in our results. But I hope that this example convinces you that these curves in the space of oriented geodesics, they are equivariant, but they come from non-equivariant curves in the space of geodesics. Unless, of course, you take the angle to be theta over 2. In this case, the geodesics are orthogonal. In this case, you are really the yellow curve. If the geodesics form an angle pi over 2, then the yellow curve will be equivariant. But in all the other cases, they are not. So any questions so far? Okay.
No, it's really clear. It's really clear.
Great, thanks. So now it's finally time to present. I will give you two characterizations of these, two answers to this problem. The first characterization is in terms of what it will be called the Maslov class. So what is the Maslov class? Let's start over with the notation. We fix an nearly-Fuchsian representation, which is always rho. And then we have these Lagrangian and Riemannian embedding, because we know these are necessary conditions, in R rho, again. So this is in the quotient. This is the embedding in this omega plus times omega minus divided by the action of the group. And you can compute this one form, which is, what is this one form? We take omega, we feed omega on one entry with h, which is the mean curvature vector, and then we pull back by g. So basically, in easy terms, this is just on our M. This is just one form, which is obtained by taking the symplectic 2 form on the image, and you feed curvature vector on one entry and your favorite vector on the second entry. And it turns out that this one form is closed, and the Maslov class is simply defined as the cohomology class of this one form in the de Rham cohomology, the first de Rham cohomology. And our first theorem is that this embedding G, in R rho, it comes from the Gauss map of, so it's somehow it can be integrated in a rho equivariant way. So it comes from the Gauss map of some I in the quotient, so in the nearly-Fuchsian manifold, if and only if the Maslov class vanishes. Okay, so the Maslov class of this embedding is precisely the obstruction to rho equivariance. If you look at things in the universal cover, is the obstruction to rho equivariance in H to the n plus 1. Yeah, so half the audience which has a good intuition of anti-de Sitter geometry will easily realize that these curves theta equal to theta 0, or theta equal to a constant c, or theta equal to theta 0, sorry, here's a mess. Anyway, these curves at theta equal a constant, the Maslov class, well, they have non-vanishing mean curvature unless, here it's a completely mess, sorry. So unless, okay, what I want to say here is the Maslov class of the curves induced by theta equal to c vanish if and only if c equal to pi over 2. So there's a huge number of mistakes in this sentence, and unfortunately, they do not compensate one another.
So basically,
anyway,
the Maslov class is equal to theta 0.
Basically, it's equal to this constant, up to maybe taking some hyperbolic, or some tangent, not hyperbolic, some other factor. Okay, so this is just to support the fact that the statement of this theorem is believable. All right, and I'll give you a sketch of the idea of the proof of this theorem. So let me just make a little reminder. So where does the Lagrangian abstraction come from? The Lagrangian abstraction came from this magic formula that the differential of omega is equal to the pool, or small omega is equal to p star of big omega. The big omega is the symplectic form. And actually, by the way, it's exactly by this formula. Maybe I should show the formula again. This, oops. So this was the fundamental formula. The fundamental formula. The pullback by p of the symplectic form on the space of oriented geodesics is the differential of the connection form. And by the way, this is one way to prove that omega is closed by this formula. So that this is actually paracalar structure. Anyway, from this fundamental formula, it followed that the Lagrangian condition, because basically the pullback bundle G sigma star of P has a flat section. Now, if we care about the equivariant case, we can actually go to the quotient, and we have a principal bundle over the manifold M. Basically, we take this pullback bundle and we quotient by the action of the group. And now one proves that the condition that our immersion is obtained from an equivariant immersion in H to the n+1 is equivalent to the condition that this pullback bundle in the quotient, PG, is flat and is trivial. Namely, it admits a flat section, which is a flat global section. It's not only locally trivializable by flat sections, but it's also admit a global section, which is trivial. And it's well known that in the theory of flat bundles, the obstruction for a flat bundle over a certain manifold to be trivial is the holonomy representation, which is basically what is the holonomy representation of the bundle. You take an element of the P1, so you take a path in your base manifold, you find a local section, flat local section, not local, sorry, I mean piece by piece, you take a flat section over your loop downstairs, but when you come back to the original point, I'm not sure if you see me, but when you come back to the original point, over the original point, you are in a different place in the fiber. And the holonomy measures exactly how much you moved in the fiber after you perform this loop. And this only depends on the homotopy class on the path, so it's well defined on the P1. And the formula, the expression which permits to prove our theorem is that the holonomy of this PG, so all is the holonomy of this bundle PG in the quotient, is precisely computed over a path alpha, is exactly the integral of alpha of the Maslov class. And therefore, the holonomy is trivial if and only if the Maslov class, which is the cohomology class of mu G, vanishes the H1. Okay, this is not a complete proof, but it's at least a sketch of how this goes through. Questions?
Have you finished?
No.
Right,
There's the second theorem. I wanted to make sure there's no questions.
Oh no, it's clear.
No. there's yet another result. I'm sorry for that, but you have to tolerate 10 more minutes of my talk. The second characterization will be given in terms of the Hamiltonian group. So here I need to give a little bit of notions of symplectic geometry before I can state my result. Now, okay, somehow our first result was a sort of recipe to decide whether an embedding in RO, again, our embeddings are Lagrangian submanifolds in RO. This was a recipe to decide whether a submanifold in RO Lagrangian comes from a hypersurface in the nearly-Fuchsian manifold. Just compute the Maslow class and see if it vanishes or not. Now, this second result will try to give a more global description of all the submanifolds which arise in this way. And for this, I need to say what means what is the notion of a Hamiltonian symplectomorphism. So a symplectomorphism, I think you know what it is, and it's a diffeomorphism, self-diffeomorphism of our favorite symplectic manifold, which is of course this one, which preserves the symplectic form, and this is called Hamiltonian if this can be obtained as the diffeomorphism by integrating at time 1 a vector field which a priori might be time dependent, which is Hamiltonian. So basically, our psi is Hamiltonian if we can obtain it as psi1, where psi t is this pet defined by integrating this vector field vt, and the vt have the beautiful property that they are Hamiltonian vector fields. This means basically that they are symplectic gradients of some Hamiltonian function. Okay, the one form which is obtained by feeding omega with vt is exact. And actually, it turns out that this vt can be taken time independent. And also, I'll say now, and I forget forever, we always consider Hamiltonian symplectomorphism which are compactly supported here. But I will not write it each time. And another well-known fact in symplectic geometry that this group of okay, first of all, the Hamiltonian symplectomorphisms form a group, and this group is also normal subgroup in the full group of symplectomorphisms which are isotopic to the identity, and the quotient is isomorphic. The quotient group is isomorphic to the H1. So this, since our previous results had the vanishing of some class in H1 as the only obstruction, then maybe it's not so surprising that the obstruction, now we will give another reformulation of this condition, but the obstruction will be exactly given in terms of certain symplectomorphisms which must be Hamiltonian, because basically this corresponds to the vanishing of something in an H1. Okay, it's very, very vague so far. Then somehow dimensionally it's kind of the right thing to look at. So this is our theorem. It's a little long to state, but let's fix the setup. As usual, we fix once and forever a nearly-Fuchsian representation. So since this representation is nearly-Fuchsian, we know there is one submanifold which is Lagrangian and Riemannian, which comes from an embedding in the nearly-Fuchsian manifold. Okay, there is one because by definition there is one which comes from here, which is the nearly-Fuchsian manifold, because by definition rho is nearly-Fuchsian, and we have one embedding with principal curvature minus 1, 1, and therefore this gives in the space of oriented geodesics something which is Lagrangian and Riemannian. Now let's pick another submanifold in the space of oriented geodesics, in R rho more precisely, in the quotient of the space of oriented geodesics, which is again Lagrangian and Riemannian. And I want to ask the question: when does also L prime come from an embedding I prime? Well, the answer is L prime comes from an embedding I prime, exactly as L does. And this embedding has principal curvatures in minus 1, 1, if and only if there is an Hamiltonian symplectomorphism which maps L to L prime. Is the statement clear?
Very.
Okay, good. So basically, what this theorem says, it says basically that the Lagrangian Riemannian submanifolds, which L prime, which are obtained in this way, are those which live in a certain orbit of the Hamiltonian group. And just to mention this, in dimension 3, if our rho is moreover almost Fuchsian, this means that we can take our I to be also minimal, then this L is minimal Lagrangian. So basically, in this special case, we can reformulate this statement. We can reformulate the whole statement by saying that these L prime, they are those which stay in the orbit of the unique minimal Lagrangian submanifold of Rho in its homotopy class. And let me give a quick sketch of the proof. I will be shortly over time. Maybe we start a few minutes later, so maybe I'm still good.
That's cool.
So here, again, we need a formula. Was this a question, Graham?
No.
Okay, good.
It's cool.
The fundamental step is to give a formula which, whenever you have these two Lagrangian and Riemannian submanifolds, N and L prime, L and L prime, we want a formula which relates the holonomy representation of the associative principal bundle of L and the holonomy representation of the associative principal bundle of L prime. And this is the formula. Basically, suppose we take an homotopy which deforms L to L prime. So this is we just move the Lagrangian submanifolds from L to L prime. And we can compute what is the difference between the holonomy. Remember, the holonomy is something which takes alpha in the pi 1 and spits out a real number. We can take the difference. And the difference is just this integral. Basically, we take omega fed with Vt, and Vt is the manifold, is the vector field, which is the variation of our homotopy. Then we pull back to M by psi t itself. We integrate over alpha, and we integrate over 0, 1. And this is the difference of the two holonomy representations. And let me just mention that this thing, the right-hand side, is a sort of manifold a sort of version for submanifolds of what is usually called the flux homomorphism. So this version for submanifolds is due to Solomon, but in a slightly different setting. The version of the flux homomorphism, usually the flux homomorphism is computed on an entire symplectic manifold. You just do the same thing, take a homotopy of a symplectomorphism, take the global vector field now, which generates the isotopy, and integrate. And this is usually the obstruction to a symplectomorphism, for a symplectomorphism to be Hamiltonian. But here we are on a slightly different setting, but in fact, one implication of our theorem is very easy, because if we have a psi which Hamiltonian, if we have some psi Hamiltonian, so it's obtained as time one integral of Hamiltonian vector fields, which maps L to L prime, then basically we can choose this homotopy psi t, small psi, to be the restriction of ambient Hamiltonian isotopy. And therefore, this Vt is the restriction of global Hamiltonian vector field. And therefore, this guy, which is under the integral, basically, since the big Vt are Hamiltonian, we have a global Hamiltonian function Ft. And since the differential commutes with pullback, we see that this guy is exact at every time. And therefore, when we integrate over alpha, this gives 0, and we integrate between 0 and 1, we get 0. And therefore, the holonomy is equal to the holonomy prime. The holonomy of PL is equal to the holonomy of PL prime. So if PL has trivial holonomy, also PL prime has trivial holonomy. Okay, and therefore we get a result. The other implication is more interesting, because we have to do something different here. We have to assume that the holonomy of PL and PL prime are both trivial. Both holonomies are trivial, and we must show that this integral is 0 for a certain psi t. Sorry, what am I saying? Sorry, by the formula, sorry, I completely messed up. By the formula, we have that by the formula I gave in the previous slide, this thing is 0. Sorry. But then we have to prove that this homotopy psi-t can be obtained as the restriction of a path of ambient Hamiltonian isotopy. Okay, and here the methods of Solomon they do not quite apply because they have more strict topological assumptions which we cannot use in our case. Okay, I have to go a little quick here because I'm getting late. But anyway, here is the great idea of my co-author, that in order to look of our favorite homotopy psi-t, which is the restriction of will be this homotopy psi-t has to be the restriction of Hamiltonian isotopy. We can choose it in our special setting. We can choose it in a very smart way, and that is we go back to our nearly-Fuchsian manifold and we deform the hypersurfaces in the nearly-Fuchsian manifold. So we can take the formation of hypersurfaces moving from sigma, which is the hypersurface whose associating Lagrangian submanifold is L, to sigma prime, for which we have L prime. And in this case, we have the usual formula, but now over this special, on this special homotopy psi-t, we have that the holonomy times T0 minus the holonomy of time 0 is always 0, because all these submanifolds which we get in the space of the oriented geodesic come from hypersurfaces in the nearly-Fuchsian manifold by construction. And therefore, we have the integral. The integral is, this integral is 0 at every time. And this means that the guy under the integral is 0 at every time. And this means that this guy is exact at every time. And therefore, we can now extend these functions, which are only defined on the submanifold, to global function. And we integrate these global functions, and these are Hamiltonian vector fields. And at time 1, we get the Hamiltonian symplectomorphism which we wanted, which sends L to L prime. Okay, sorry, maybe it was very quick, but just a sketch of this proof. Probably everyone got lost. But I can now finish by saying something about this question of the flow defined by Ben Andrews. So in fact, in light of our first two results, now it's a very natural question to ask. In the first result, we had this Maslow class. So we basically fed omega with the mean curvature vector. And in the second result, we were feeding omega with some sort of Hamiltonian vector field, some sort of whatever. And now the natural question is, what happens if we take this deforming vector field of our homotopy to be exactly a mean curvature vector field, and this gives the mean curvature flow in the space of oriented geodesic, or more precisely, the Lagrangian mean curvature flow. And this is what relates with the flow which was suggested by Ben Andrews. So basically, if you evolve in hyperbolic space, this is a very local result. In fact, there's no group action, nothing. If we evolve in hyperbolic space by this flow, by means of this weird function, which is the sum of the hyperbolic inverse tangent of the principal curvatures, and then you look in the space of oriented geodesics, this induces the mean curvature flow up to some tangential deformation. Well, this is something maybe I have already said, answering Graham's question. This flow in hyperbolic space is sort of the analog of other flows which have been defined in the n-sphere, in anti-de Sitter space also. And in these other settings, there was a similar relation with a certain mean curvature flow with respect to the correct metric in the space of oriented geodesics of these other spaces. Okay, this is so the somehow an answer which gives a geometric interpretation to this and flow suggested by Andrews in terms of the space of oriented geodesics. And yes, thank you very much for attending.
Thanks for that. I really like that. Well, I've got lots of questions, but first I'd like to ask if anybody else has any questions.
It's kind of scary, right?
Sorry?
It's kind of scary for the other. It's like, do not have question because I will ask for half an hour.
No, don't worry. Don't worry. I'm enjoying
I
this.
think that I have some questions.
Go ahead, Roman. Go ahead. Do you mind turning on your camera so we can see you?
Yeah, I guess so. Does it work?
Yeah.
Okay, great. So first question I want to ask, so if you have an almost Fuchsian manifold in dimension 3, for instance, and a minimal surface there, so it's possible to restore our almost Fuchsian manifold based on the internal geometry of the surface.
To describe the almost Fuchsian manifold in terms of the geometry of the surface?
So I mean, if you have a surface and we know that it's a minimal surface in an almost Fuchsian manifold, so is this almost Fuchsian manifold unique?
Okay, so there's two things I think. First, if you have almost Fuchsian manifold, so it contains a minimal surface with principal curvatures between -1 and 1, then this minimal surface is the unique minimal surface in the homotopy class.
Yeah.
Okay. And second thing is, yes, so if you know the first and second fundamental form of the minimal surface, then of course this determines uniquely the geometry of the entire manifold. Because basically you can evolve normally, and you can see that there is a unique such, but this is even in more general.
Yeah. But actually, from just the first fundamental form, is it possible to restore it only from it?
Only the first fundamental form. Sorry.
Yeah.
Only the first fundamental form. I'm not sure. Probably yes. I think.
It seems unlikely because normally you use two surfaces to define the sort of manifold.
I would be inclined to.
Yeah, but I mean, so the surface there is not hyperbolic internally, so it carries more data rather than a hyperbolic surface. So a quasi-Fuchsian manifold should be determined by two hyperbolic surfaces. So if you have a surface which carries more complicated data rather than just hyperbolic geometry, then maybe it's possible to restore it.
Yeah, but dimensionally it doesn't strike me as realistic. I realize everything's infinite dimensional, but it doesn't.
I would be inclined to say yes, but I'm not sure. Yeah, I'm not sure, but I don't have a clear answer. Sorry.
Okay, so I have another question. So if I understood well, so almost Fuchsian manifold constitute a proper subset of quasi-Fuchsian structures. So there are quasi-Fuchsian structures that are not almost Fuchsian, right?
Yeah.
Okay, but is there anything special about structures on the boundary of almost Fuchsian structures inside quasi-Fuchsian? So
it's a very good question, but it's not so easy to answer. So in fact, I think not so much is known on the locus of almost Fuchsian manifolds inside quasi-Fuchsian manifolds. What I can tell you is, for instance, that in my PhD thesis, I showed that basically, if you look at the space of quasi-Fuchsian manifolds as the product of two copies of the Miller space by the burst parameterization, then basically it proved that almost Fuchsian locus contains a uniform neighborhood of the diagonal with respect to the Miller metric.
Mm-hmm.
Then what I can tell you is that Andy Sanders proved that you cannot degenerate in quasi-Fuchsian space to a doubly degenerate limit of quasi-Fuchsian manifold by staying almost Fuchsian.
Mm-hmm.
But you know, these are partial results, but they are very far from giving a complete answer to your question. I think your question is very intriguing. I've been intrigued by this question for a long time. And yeah, I would be very happy to have a satisfying answer, but so far I think there are partial results.
Okay, but is it actually conjectured or known that it can touch the boundary of quasi-Fuchsian deformations in any other way rather than doubly degenerate? Okay. Okay. So, and maybe the last question. So, a quasi-Fuchsian structure is a quasi-conformal. So, its action on the sphere at infinity is a quasi-conformal conjugate of a Fuchsian representation, right? Is there anything special about this quasi-conformal map in case of an almost Fuchsian structure?
I think it was a very good question. I don't know. Yeah.
Okay.
I don't think it's a very easy question, actually. Yeah, it's a good question. I think you want to somehow understand whether the quasi-conformal conjugacy has some sort of special regularity when the representation is almost Fuchsian, but I don't know.
It would be interesting.
I'd love to have an answer one day of all these questions.
Okay, but thank you very much for the talk.
Thank you for the questions.